Major earthquake at 10:23 a.m. local time on July 11, 2024. A major magnitude 7.1 earthquake struck just west of the island of Mindanao in the Philippines. While many people might have expected severe damage and possibly even a tsunami to have soon followed, neither of these happened due to the strange nature of the earthquake which had just struck. This earthquake did not occur in the crust, but instead the very bottom of our planet's upper mantle. This caused a number of strange phenomena to be observed, the least of which was the fact that the area directly above the epicenter experienced the least intense shaking. Underneath the southernmost tip of Mindanao, the Philippine Mobile Belt is underlaid by the very northernmost edge of the Molucca Sea tectonic plate. The earthquake which struck occurred within a superdeep section of the subducted tectonic plate slab at 620.1 kilometers or 385.3 miles depth. Thus, while both the slab and the surrounding mantle are solid, the slab is slightly colder. Since colder objects transfer seismic energy at higher speeds, the slab acts as a conduit which transfers energy more efficiently to the overlying landmass than the oceanic crust directly above the earthquake epicenter. But why did this earthquake occur in the first place? After all, in the upper or lower mantle, there are not fault lines that we traditionally associate with the crust of our planet. And this is mostly true. However, faulting can occur on the subducting slabs since they are in essence sunken portions of what was once a piece of crust which could produce earthquakes. As to the specific trigger of the earthquake, it involves phase transitions. Since the subducted slab of the Molucca Sea plate is a piece of oceanic crust, it is almost entirely composed of basalt which in turn contains abundant olivine. As olivine slowly travels deeper into the phase transition's planet's interior, it reaches several thresholds of pressure and temperature at various depths that cause the mineral to transfer into other minerals with more stable crystal structures at those conditions. While olivine is fairly stable all the way to 410 km depth, a little deeper than this it changes to the denser mineral wadsleyite. Wadsleyite is stable from 410 to 520 km depth, until it changes to the even denser mineral ringwoodite which in turn is stable at 520 to 660 km depth. Yet, if you go any deeper than this while still remaining in the lower mantle, ringwoodite decomposes to bridgemanite and ferropericlase. Each of these phase transitions causes what was originally olivine to become denser and denser, and each time this change occurs it creates a zone of very finely grained material between rows of relevant larger crystals. This process occurs in the transforming wedge of a subducting slab. Thus, when residual stress from the uneven pull of a slab in the mantle builds up, the shear zones with many fine grains formed by phase changes are the first to slip, generating so-called deep-focused earthquakes. Yet, this transforming wedge region is generally not very thick, only theoretically earthquake triggers suitable for generating up to magnitude 3.8 earthquakes. So, how do larger earthquakes occur? The answer is that sometimes, if enough of a slip occurs, it can near instantaneously trigger motion via transformational faulting in the stable part of the subducting slab. Yet, this process can only create up to magnitude 6.8 earthquakes. Even larger earthquakes occur when the prior two processes occur, and then trigger a third event, where a region with more heat generated by deformation than can be conducted away also slips in what is known as a thermal runway. Thus, thermal runways allow for the largest deep-focus earthquakes to occur, such as what was recently witnessed in the Philippines. As a final note, I would like to thank my new patron Jisoo Kim for supporting this YouTube channel.